Hello, my name is Caitlin Holt. I am a mathematics major from the University of Mary Washington, and today I will be presenting my research on the numerical study of the SEIQR model for COVID-19. So for this presentation, I will be talking about mathematical models for epidemics, my analytical solutions to the model I was focusing on, the numerical methods that I used to find a numerical approximation to the model that I was focusing on, as well as some hypothetical examples to explore what happens when we change our parameters. So we're going to talk about our mathematical models for epidemics. So the first model that we're going to talk about is the SEIQR model for epidemics, also known as the SEIQR model. And here we have our three differential equations with our susceptible, infectious, and recovered populations. And we have two parameters here, which is beta and gamma, where beta is our transmission rate and gamma is our recovery rate. So in order to make this more complicated, to go with all of the stuff that we've seen with the COVID-19 pandemic, we found a model that has more populations to take into consideration all these different factors. So when we extend this model for COVID-19, we now have 7 equations, and we can now look at a diagram to show how all of these populations interact with each other in an easier way. So now we have our diagram here, which has all 7 of our populations, and we have 6 parameters this time instead of just 2 for our regular SEIQR model. So when we start with our susceptible population, we can see that people can either become insusceptible or exposed to the virus. And if they're exposed, that means they have tested positive, but they don't have any symptoms yet, and they can't spread it to other people, so they're not contagious yet. But once they are in this exposed population, then they can move to the infectious population through our gamma here, which is the amount of time it takes for them to develop those symptoms and they become contagious. And then once people are infected, they will move to quarantine through our delta parameter, which is the amount of time it takes people to move into quarantine once they discover that they are contagious. And once our population is in quarantine, then they can either become recovered or die from the virus. And those who recover are transferred using this lambda parameter, and those who die are transferred using this k parameter. So now we're going to talk about some analytical solutions. So why are we using analytical solutions and what are they? So analytical solutions are also known as exact solutions, and they can help us understand the relationship between variables when we find our solution. And the computations are usually faster than numerical solutions, which are more iterative, whereas analytical solutions, once we find it, we can just plug in the numbers. So in order to find the analytical solutions for our model, we did create a simplified model since we were not able to find a solution for all 7 equations. So we simplified our model down into the exposed, infectious, and quarantine populations based on these 4 assumptions. We assume that no immunity is developed. The cure rate and the mortality rate are both constant, so we don't see any change over time in the rate for mortality and the cure rate. And also our last assumption is that we don't have any new infectious, closed, or recovered cases. So taking all these assumptions, we do find that our lambda becomes 0, our k becomes 0, and our beta, which is our infection rate, also becomes 0, which brings us this simplified model here. So in order to find the solutions to this simplified model, we did 3 steps. First, we solved for EFT directly through integration. And then once we had EFT, we were able to solve for IFT using a technique called integrating factor from differential equations. And then once we found IFT, we were able to solve for QFT using a similar method we did to solve for EFT, which was pretty much through direct integration. So once we take all 3 of these steps, we now have our solution to our simplified model. We have our EFT, IFT, and QFT, and we do have a few constants here from our integrations. So C1 is simply, we found that from plugging in t equals 0 into our IFT equation and solving for C1. And we did the same thing for our C2, where we plug in t equals 0 and solve for C2. When we graph this simplified model, we can see the results in this figure here. So we have our blue line here is the exposed population. The red line here is the infectious population, and the yellow line here is the quarantine population. We can see that over time, our exposed and infectious populations both decrease, and our quarantine population increases until it stabilizes around 7.5 million. So our exposed and infectious populations are exactly what we would expect since our infection rate is 0. So we do see a little peak here in our infectious population, but this would just be if people are quarantined together in the same household, they may spread it within each other. But after that happens, we just see this downward pattern here in our population dynamics. So we do see that this stabilizes around 7.5 million, which is equal to our initial population of people in the beginning. So since we got rid of the recovered and population who die, we are pretty much left with people in quarantine and they don't move from there. So that is what we see when we have our simplified model. Now we want to look at some numerical methods for solving for the approximation to our entire SEIQR model. So why are we using numerical methods? It's because, like we just saw, it's not always easy to find an exact solution for every model, and it might not be possible. And so these numerical methods are less time consuming to apply than our analytical solutions because we might not always have one. So the method I'll be talking about is Euler's method, since we are a little short on time. So the first order of Taylor's method is Euler's method. So we start with an initial value, alpha, and we use this to find W1 and W2. And so we use this to find our next value. So if you want to find W1, then we'd have I is equal to 0. So we take our initial value here, alpha, and plug in T0 and W0 in for our function, and we multiply that times h, which is our step size. So that's just the number of times we're going to be. That's our step size. Okay, so our algorithm for Euler's method is as follows. We set the initial conditions and parameters. So we have all 6 of our parameters here and all 7 of our populations. And S of 0 is just time is 0. So we just have our initial populations here. And for the next step, we just repeat the next 2 steps, steps 3 and 4 for our number of iterations that we do, which is n. So our step 3 is to set all of our equations up like we just saw for our other definition. So we're going to set time is equal to the minimum time, which in this case would be 0, plus I times our step size. And then as we're moving through, we have all 7 of our populations, and we're calculating the next population using our derivative functions that we see down here from our original SEIQR model. And then once we go through all of this, we'll take all of our outputs from going from I to N, and then we'll stop our algorithm. And when we do that, we have this chart for Euler's method. We have our susceptible population in blue, our exposed population here in light blue, our infectious in red, our quarantined in this bright pink color, our recovered in green, our closed cases is here in yellow, which may be a little difficult to see. And we also have our insusceptible population over here in black. This is a zoomed in graph so that we can focus on our susceptible, infectious, exposed, and quarantine populations, but we can see that our peak for our infectious population is just around 25 million, and our peak for our exposed populations is around 10 million, and our peak for our quarantine population is just between 15 and 20 million. So what happens when we find different parameters, and how will this affect our graph? So we're going to talk about some hypothetical examples, and these are really important when we want to investigate what happens when we change our parameter values. So for this presentation, we're going to be exploring what happens when we change the infection rate, the protection rate, and the quarantine rate. We're looking at these values specifically because these are ones that we can more control ourselves, that don't have to do with the properties of the virus itself. So first, we're going to look at what our original reproduction number was. So the reproduction number takes into consideration the infection rate and also our protection rate. So this is our original graph that we just saw a second ago when we were doing our numerical method for Euler's method. So we have our beta here is 0.9224, and our alpha here is the 0.1475. So alpha is affected by the amount of time that people are wearing masks and social distancing and pretty much taking precaution around others when outside of their house just to stay safe for COVID-19. And our beta here is found from calculating the average number of infectious people. Imagine the average number of people who are infected by someone who is infectious with COVID-19. So we can see our original graph here. And then when we increase our infection rate, we have our peak for our infections increases to almost 40 million, whereas before we had it at 25 million. And we can see our exposed population also increases, as well as our quarantined population. So now let's see what happens when we decrease it. So this is what happens when we increase it. And now when we decrease our beta to 0.75, we can see this peak decrease to around 15 million, which is even better than what we had before. So our protection rate is also significantly higher, which is definitely a reason for this. And we can see our exposed population is also significantly less, as well as our quarantine population. So now we're going to see what happens when we change the quarantine rate. So this is our original quarantine rate. We're saying it takes about 14 days for people to quarantine once they realize that they are contagious. This is kind of based on what the CDC recommends, that people quarantine for 14 days. So we can see our original is at 25 million for infectious, around 17 million for our quarantine. We're going to really want to focus on these two colors here. So in our next graph, we see that when we decrease the quarantine rate to just 10 days, we can see that the infectious and quarantine populations are almost equal peaks for these two different time frames. And we see that the number of infectious people decreases to below 20 million, and our quarantine population is also about the same. So now when we see what happens when we decrease it to, say, 5 days, we can see that our infectious population is significantly lower and our quarantine population is also lower, but we see that this difference here is almost twice as much between our infectious population and our quarantine population. And with these parameter changes in mind, we can draw some really interesting conclusions about taking these different precautions for COVID-19. So in conclusion, during this presentation, we obtained an analytical solution to a simplified model of the SEIQR model. We generated some numerical approximations for our entire model itself. And using those approximations, we were able to change the parameters and just see how important it is to take precautionary measures and to lower the number of infections there are for COVID-19. Thank you. Are there any questions?